So we're doing, let's see, we've got 431 there.
Yeah.
Are you all done with that?
Yeah, it was just like adding up the
Okay.
stuff.
And that one is, where is that one?
It's the third page.
There we go.
Second page.
F431, okay.
Yeah.
So F431 is asking you to find an equivalent resultant force and locate it on the line of action where it intersects the beam measured from point O. And you did it by adding up all the forces to find the resultant magnitude, right?
Yeah.
And then you know you got to put it somewhere a distance xr away from the origin, right?
Yeah.
And that position has to satisfy the condition that the sum of the moments about the origin in both systems is equivalent. So you do the moments in system 1.
Yeah. And we already know what FR is.
Yep.
System 2, so I guess this is.
And you know FR for system 2. You just got to find XR, the location of it. And so you set up the equation and you solve for XR. 6 feet looks good. That's the correct answer. Great. That one's easy.
Yeah.
40.
And 26 is you are replacing it by an equivalent resultant force and couple moment acting at point A.
Oh.
So you got the picture there, you're finding the force in X. So the moments are about A is minus 30 times 3.
It's 40 times 0. 30 times 3. Is this the other one? Is this
Minus 30 times 6. Does that seem right?
David, why'd you put 30 times 6?
Isn't that the distance from A to that force?
50?
It's the Y component.
It's the Y component, because the X is along the moment axis.
Right.
So only the Y is acting on it, right?
You want to?
So in other words, that's 30, right?
Oh, right.
And this is 40.
Yeah, just do that one.
Why is that 40?
4 over 5 times 50.
But this isn't in newtons. This. I
What?
thought that was like a distance thing.
Say that again?
These don't have units on them.
These don't have units on them, but this does. What is that?
That is newtons.
That is the hypotenuse of that triangle.
Okay.
This is a similar triangle, which is dimensionless. It's just telling you the ratio of sides.
Ratio.
This is a unit, 50 newtons times 3/5. It's going to get you
30 and 40.
30 that way.
It's not
40
actually a
that way.
distance though. It's just
What are you talking about, a distance?
like it's not
It's a-
actually like a
it's a-
triangle that's like 30 units this way, 40 units that way. It's not like that.
It is like that,
It is,
except the units are newtons.
but I thought
It's not distance, it's force.
it's not in distance, it's force.
Yeah.
Okay, that's what threw me off.
Yeah.
When I think about a triangle, I think in distance.
Well, we've been dealing with triangular related to forces too. Just another unit. Okay, so the moment is what?
Wait, so David, is this just like the total moment, or is that just?
I don't know if I wrote that right.
Yeah, it's the sum of the moments at A. That's what that means.
Okay.
Sum of all the moments about point A.
Okay.
You got a moment from here, which is 0. A moment from there, which is 30 times 3. A moment from here, which is 30 times 6. And a moment from there, which is 40 times 0.
Right, because it's along the axis.
Yeah.
Okay. And then what about this?
What about it?
Oh, we broke it into this.
Yeah, you broke it into that and that.
And then what about
So
the
that's
torque?
this.
Oh, there's a moment there at the end. Look at that. There's a couple there at the end.
Okay.
Can I have everybody's attention here? This is something that everybody like does no idea what this is. Like, you got a curly Q at the end of that beam. What is that? What is that?
A pre-existing.
Is that the first time we've seen one of those? It's a special kind of moment. What kind of moment is it?
Couple moment.
A couple moment. Okay. What does that mean? The tendency to rotate. That means there's a force couple there. And when you see one of those, they're not a mysterious force that we have no idea what that is. They are a couple. Okay, and you could always draw that as a couple. So when you see 200 Newton meters there, just because this is so strange, you could think of it at the end of this beam as being, right? You could either have a 200 Newton meter there, or you could have a couple there where you have like 100 newtons spaced a meter apart. A 100 Newton couple. So, or a 200, or say, I'm sorry, 100 Newton spaced 2 meters apart, or a 200 Newton force spaced 1 meter apart, or a 1,000 Newton force spaced a fifth of a meter apart. Let me show you what I mean. So you could have that, or you could do it like this. Now, how does that couple apply? Well, it could be, let's see, which way is it going? It wants to make it go this way, right? So you want to actually have a rotation that's sort of clockwise. So maybe you have a force going up here and a force going down here. And if this was 200 newtons, and this was 1 meter, and this was 200 newtons, these are, again, equivalent systems. Except a meter is kind of far, and on this scale of this thing, it's kind of a little bit weird to have a meter, but it could be, or it could be 0.1 meters apart and 2,000 newtons. I don't know, it takes a while to kind of get used to this. I was a little puzzled by this thing the first time I saw it. It looks a really mysterious thing, but it's a sense of trying to twist that thing at that point, right? And it's telling you the torque or the moment of that. And if you ever wonder how to process this in a future problem, you can always take and draw that as two forces that are opposing each other as a couple of a certain magnitude. And then it's kind of easier to understand how that's affecting the rest of your system, because you can add up forces. Of course, the forces add up to 0, but you can see there's going to be a net moment from that thing, right?
How do you know how far they are apart?
Doesn't matter. You just scale up the force so that the product of the force times the separation equals 200, right? Could be 20,000 newtons separated by 0.01 meters. Still going to have a moment of 200 newton meters.
How does that factor into the answer, or into the rest of the equation?
Well, you have to sum all the fx's. Well, there's no x components on that, and if you summed all the fy's, they would cancel out, right? So they don't affect the sum of the forces, right? But they do affect the moments at A, right?
So you add 200 meters.
Ultimately, that's what you're doing. You're going to add 200 newton meters at the end. But it's actually going clockwise, so we would actually call that minus 200 newton meters. That's because of that, right? So, yeah, that's a thing to kind of get over. Again, the more you use it, the more you do these things, the easier it gets.
What is this angle? To give an answer?
That is the angle of the resultant in the answer. So in other words, you're supposed to specify the magnitude of the force and its angle from the horizontal. Does it tell you that?
Use trig. It doesn't ask for it.
Well, equivalent force and couple moment acting at 1 day. Well, that's what the answer is. So the magnitude of this thing should be 108 newtons. So how are you going to know if you got the right answer? We'll find the magnitude of that. Of your net resultant.
We use like Cartesian to find angle, right? Like having
Arctangent of Fy over Fx. Yeah.
Will Fx be negative
I don't see a negative here. I just see a positive force.
What was that?
Like, is it right?
Down. The force.
The y force is down, yeah.
Oh, okay.
But the x force is going to the right. Yeah.
Is it counterclockwise or just clockwise?
What? Fx is a force going horizontally. Why are you talking about clockwise? Couples and moments are clockwise or counterclockwise, but forces are either, in a line. They're either horizontal or vertical. Okay. Guys are talking crazy on me again. So that's up to 100. Looks like it. So square root of 100 squared plus 40 squared should be 108. Does that sound right? Probably. Huh?
Square root of 120. Oh, 100.
Square root of 100 squared plus 40 squared.
Okay.
Then the angle means 68.2 degrees, I guess, from the horizontal, which seems reasonable again.
But if the y is going down, how would the angle be positive?
Those are moments.
Well, if you're just talking, say, the angle from the horizontal, right?
Okay.
I think what you're supposed to do is
So that should be something like that.
Should it be negative 68?
Fine.
I think you're supposed to find
Should be negative 68.
Classically.
the area.
And the m is 470, is that right? You got 200 there, you got 180, and you got 90. 180 plus 90 is 270, right? Plus 200 is 470.
This is one
We
you
just want to have some that
No, I'm talking about the moments.
So
are going down that represents all of this.
90.
We want to have.
So draw the equivalent system then. You're doing the equivalent
So
resultant force and couple moment acting at point A.
So we have to, I think, yeah, we can just. Yeah, but these are moments, so you have to
Mhm.
multiply them all by their respective distances to get the, yeah.
Questions? I prefer you to be more engaged.
Yeah, so you can say.
But if that's how you like to do it. I don't want you to feel like you're shut out here.
Yeah.
When you actually
So
start
6
doing it, that's when
kilometers.
you.
Wait, what? So, since it's a moment, we know what the moment is 6 kilonewton meters. We want to know what the force is. So then if we want to know, so that means the F is equal to this divided by
And what else?
5 meters.
Yes.
Yeah, so I don't know what's that.
Good.
6 divided by 5.
So,
This just makes sense.
does it make sense?
Yeah.
square.
No, because the answer is like 40 kilonewtons, and this isn't gonna add up to.
Yes, sorry.
40. This is the thing where you have to use like you have to find like the area or something like that. Under
Oh, yeah.
like
He's graphically representing.
yeah, something like that. Let's see. Because like in this problem, they have this
And that's acting on
they have
the
this
beam.
rectangle here, and so they found the base was the 3 meters long, and the height was
Okay.
0.5 kilonewtons. So then, I mean, it's technically like an integral thing, but you don't have to do that because it's just a rectangle. And you know how to, we know what the area of a rectangle is. So
when you add them all up,
I think you just sum up the areas of the rectangles to give you the FR.
For each rectangle, yeah.
Yeah.
The area, and then it's located right in the middle. Area located in the middle. Area located in the middle.
Yeah.
Yeah.
How do you know what the height is though?
The height of what?
Like if we want to call these things rectangles, like we know what the base is. What do you, is the height just the
Yeah.
3 kilonewtons?
It's how intense the force
okay.
is.
Okay, yeah.
Yeah. Because when you take the product of that times the width, you're going to get a unit of kilonewtons.
Right. Okay. But are these like? Is this like pressure or something? Or is
Yeah.
this,
It's they call it intensity. Pressure is like kilonewtons per square meter.
okay.
What we're saying is if you factor in, like they've already sort of integrated along the depth axis.
Yeah.
So that got rid of one of the meters.
Okay.
And now you're just left with kilonewtons per
Okay.
meter.
Let's see. Yeah. So I guess if we wanted to say this was like a rectangle, and this was a rectangle. This is a rectangle.
Yep.
Then you can say this is 1, 2, 3.
Mm-hmm.
So then 1 is going to be 6 kilonewton meters,
That's the F.
5 meters.
You could call it F1. Not just
Oh,
one.
yeah, not just one. Yeah, F1.
6 kilonewtons per meter times 5 meters. Or
So
1.5
what's that?
meters.
9?
9 kilonewtons. And X1 would be where it's located, is going to be at, all the way from the left, is going to be at a location of,
1.75?
yeah.
Right? Halfway?
Yeah. Yeah, so you say X1 equals 0.75.
Okay. But do we need to, yeah, I guess we, yeah, okay.
You need to keep track of those eventually, yeah.
0.75.
Meters, yeah. Sorry?
How did you find X1?
X1 is the midpoint of that. Because it's a rectangle, the equivalent location of that. So in other words, you're reducing that rectangle to a single force, it would apply right in the middle. If it's a triangle, it doesn't. It applies a third of the way over from the big edge. So just as you'll find in the lecture, if it's a triangle like this, which is maybe 6 meters on the bottom and 3 newtons per meter on one side, the FR is going to be 18/2, right? Half base times height. And the location, XR, is going to be 2/3 from the point, or 1/3 from the big side.
This distance, right? These games.
So it's going to be 4. Yeah, that's the distance that you're pointing to there from the left side of that force distribution.
But for like the second one, when we want to find X2,
Yeah.
it's not going to be just like half
No,
of
you,
this, right? 'Cause
you
we
have
wanna
to
measure it
reference
from-
everything to the same point.
Right,
It could be
okay.
here, it could be in the middle, it could
Okay.
be there, but you've got to do everything to the same point for the calculations to work
Okay,
out right.
cool.
So X2 is going to be, what is this thing? It's 1.5
Plus 1.5.
plus 0.75. Oh no, 1.5 plus 1.5. Yeah. It's 3 meters. That worked out okay? Did the arctangent?
Yeah.
So this is, so then this would be, so this would be 4.5 plus half of this. So 5.25, because we have to reference it here. Like A.
Is there a question?
Okay.
Well, we were wondering if you picked the point here instead
Well,
of here and you had other distances.
You did the moments about another point instead of the origin?
Yeah.
Would you still get the same answer?
Not like, let's say we have the
Yeah, you
moment
could say
here.
it's like in the middle or right
He was
there.
wondering if we have these on this side,
I
we would just
don't know, I
subtract
put it
them,
here 'cause that's where I
move it to F.
Yes. And that's a good,
So that's 0.25.
it is a good practice to kind of try that, right? So suppose you picked this point right here. Call it P.
P.
But it still has to be an equivalent system at P as well as O, right? It has to be equivalent everywhere. So if you did the sum of the moments at P, I mean, when you reduce this force to a single thing, you're going to get the same answer. Only the XR will be relative to P now instead of relative to O, right? This is XRO. And if you have a P here, you can then find XRP. If you just but you got to reference everything from P then, right? So some of the moments at P is going to be
Now we know what all the
500
that means FR.
times 3. And now we're going to have to worry about signs. In this case, we could ignore signs. And in this case, we're sort of assuming that a clockwise moment is positive because we didn't put any minus signs here. Wait a second. Why? Oh, these are forces. Sorry. Here you got 500 times 3. You know, normally we would say these are clockwise, so we put a negative sign in front of them. But if they're all in the same direction, you don't have to really worry about that, right? But you can make that clear by indicating something like this.
Right.
In that case, you're considering moments that are going clockwise positive, so you don't have to worry about all the negative signs. It's just kind of pointless anyway, right? But in this case, just because we're going to have some that are positive and negative, it might make more sense to put our standard reference of a moment as being counterclockwise. In that case, the 500 pound force here is going to have a moment of what about P?
We already know what FR is. So
Sorry? 6. Why did you get 6? The moment, right? Moment is force times distance.
by adding them, you have to.
So the moment of this 500 pound force about point P is going to be what?
-3. -1,100.
Negative what?
1,100.
1,500. Why? Because 500 times 3, right?
Yeah.
So we wrote 500 times 3 right there. That's the magnitude, but is it positive or negative? If this is my reference direction for a moment, is this force right here, is that giving us a positive moment or a negative moment about P?
Negative.
Why?
Wait, but if you know,
I mean, I see the force is going down, so.
The force is going down, but that has nothing to do with the sense of the moment.
Since you said that the moment is that way,
I said counterclockwise is going to be positive.
so that it's going to
Is this going to give you a counterclockwise rotation about P or a clockwise rotation about P?
This distance is 1.5.
Counter.
When you cancel out the units.
Yeah, you see it, right? Because if this was like a water wheel or something and you had water flowing like that, this thing would want to spin that way, right?
Right. Yeah.
That's how you know.
Yeah, and since you specified that counterclockwise is positive,
Counterclockwise is positive, so we put a plus sign right here.
times the distance from A.
Okay, what about the moment of 250 about P?
Yeah.
it's going to be 0. This is
Times what is this point?
Do you agree?
Log is 0.
Why 0?
because the moment, yeah, it's right there.
Yeah,
so it's going to
yeah.
be times
Because
0
why?
since it's no length from P.
Why did he say? What did he say? Why is that 0? You say it.
Because it's at the point that we're trying to.
Because the moment arm is what?
Or 3.75.
The moment arm is not P. Remember, to calculate a moment, it's F times D. And D is how far that force is
So we
orthogonally. Yes, that's why it's 0. So you say 250 times 0, and it's 0, so you don't really care about the sign. And then the other force here is 500 for the moment arm of what? It's the moment arm of that 500 pound force about P.
Yeah, that's what I think. That's what these are, right? Yeah. Yeah. So this. Yeah. So this is actually 3. Yeah.
500 times
500 times 3.
I'll keep thinking 6.
And then this is all.
Well, don't think the 6 anymore. It's a force times a distance. That's what a moment is.
So if this was a
And is
force
this-
here,
yeah.
can you do the force times the distance between this and this?
Wait, if there was a force here
Yeah.
of 100 newtons
Yeah.
That would
or
be
100
6.
pounds,
Yeah. And that'll
what would be the moment of that force about P?
100 times 6.
Yeah, positive or negative?
Negative.
Good. But it's not, so we're not going to put that there. But this one, so the moment of this guy about P is what? Negative what?
Figured out what all
Positive.
the forces were from there.
Negative 1,500, right? So what does the net moment about P equal?
That one, I don't know.
In this
it had
case.
the circuit thing. I was like,
0.
0. Okay. Now we know our resultant hasn't changed because it's still the sum of these forces, so it's still 1250. And we've got to locate this force so it has the same net moment about P, right? In this new location, we have to figure out what's the distance from P for this resultant, right?
Right.
So in other words, FR times XR sub P about P, resultant about P, has to equal, in other words, the sum of the moments at P
Well, these aren't.
has to equal, in this case, FR times XRP. The way I've drawn it, that's going to be negative,
Or something like that.
and that has to equal the sum of the moments about P from the first system, which was what we calculated over here, all these separate forces, which is 0. Therefore, XRP equals 0 over FR equals 0. Is that the same answer as the previous one? What was XR in our previous one?
6.
6. Is that the same answer? Well, the numbers are different, but is it when you look at conceptually, is it telling us
Oh,
the
yeah.
same? Is it telling us the same thing?
Yeah, pretty much.
Yeah, because
we kind of
XR
use
XR from this previous analysis when you did the moment about 0 said XR has to be at 6 from 0.0. And we chose P to be 6
6.
from 0.0. So they actually are in agreement. Even though the numbers are different, they are in agreement.
Right.
Yeah, so it doesn't matter where you decide to pick the point to do the moment about, but you have to have an equivalent system no matter where you choose.
Kind of matter which station you have this one. Like let's say instead of making this positive, you have it that way.
Well, if you did make that negative, then you would have to do your summation negative for this one too. So if you did it this way, then this becomes negative,
But it would essentially
this
give you the
becomes
same thing, right?
negative. Wait, what? This is 0 anyways, it doesn't matter.
Oh, no.
And this becomes positive, right?
Yeah, it essentially gives you the same thing.
But then this would go away. It matters if it's non-zero, right? Because you got to make sure that you're using the same convention
Yeah, of course.
for this one as you're doing for this one. So this has to be minus, and then this becomes FRXRP, blah, blah, blah.
Long using the same sign.
Yeah.
Yeah.
Cool. That means that XR.
What you guys doing?
75.
You found F2 was 9 times 3, 27 newtons, kilonewtons, and X2 is 3 meters. And then you found F3 is 3 times 1.5. X3 is, you got 4.5 plus 0.75, 5.25.
Yeah, so that's right. Because so it's the answer just gives you it to the right of support A. I mean, this is technically right if our A is like at the very end, but it's the same thing, but their values or their reference points different. So
What's the same thing?
so like I was stumped for a second because we set the moments from
System 1 to be the
system
same
1 to
as
system
system
2.
Yep.
And we already have FR, so we just solve for XR.
Yep.
And then we get this 2.75 meters, which
Why is there a subtraction there?
because
Shouldn't
2.75.
this be 11.3 divided by 40?
Yeah, which will give you 2.75
Why is there a minus 1.5 then?
because 1.5 is the distance from A, and the answer is given and.
Oh, because it asks you to find the answer
the right of A?
from A to the right of support
so
A. Yes.
technically, yeah, that's if you add these two things, it's 2.75.
Yes. Okay, that could easily mess you up though
Yeah,
if you're
yeah.
not careful, right?
Yeah.
So to be safe, you might have decided instead of doing the moments about the edge there, you could have done the moments about A,
Yeah, that would make more sense.
and then you would have found your answer in terms of that.
Yeah, it would have been all.
Okay. Now you've got the old cement slab problem. By the way, I have a question. Who's a civil engineer majors? Just one? There's a project that this guy at the he knows some people at the city. They want to do some like water flow tracking during the storm season, and they're looking for people to kind of help out with that. I don't know if you'd be interested in that. Well, it's going to happen to be at different times, I think, but he's going to meet with, I was just kind of curious if, and you don't have to be a civil engineering major to do this if you're interested. I think it'd be going out taking measurements of like rainwater or flow depths. They were talking about setting up some instruments out there to kind of track the flow of water. You be down for that?
Yeah.
Anybody else? It would be more than a field trip. It would sort of be like an internship. I don't know if it's paid or not. I could ask them. He said they would need people from like October to April, like the rainy season, to periodically go out and take measurements and stuff.
That'd be cool.
Okay.
Especially if they-
Yeah.
Okay.
Yeah.
Thank you, Matt. Thank you, Matt.
All right. I will.
No problem.
I'll tell them that you guys are interested. Cool. Looks like everybody's interested pretty much. especially if money's involved.
The whole classes.
They have this thing called, I don't think this is involved, but the sanctuary does this thing called first flush, when there's the first big rain, they kind of measure how much pollution is going into the bay and everything. It's kind of cool too.
How do you do this already?
The slab problem. How do you do the slab problem?
Very excited.
I don't know how to do it.
So I'll give you a hint. You add up the forces to find the resultant. What are you doing to your knuckles?
Okay.
Does that like benefit you in some way?
I don't think so.
Listen, that's why he's so tall.
Some
Okay,
guy
so-
like cracked one hand his whole life and did crack the other one.
That's the
But-
So
dedication.
he was the control, huh?
Yeah, he was.
The end. And so yeah, so you've got to find, basically what you're trying to do is you're trying to find what is this, you want to reduce that to a single force, and the question is, where are you going to put it? So in other words, you're going to replace that distribution of forces with a single FR, and how far should that be from the x-axis, and how far should that be from the y-axis? XR is the distance from the y-axis, YR is the distance from the x-axis.
So we find the moment to find the resultant force that placed over it.
Yes. Now you could do this using vector moments if you like, or scalar moments. Remember how we did scalar moments, where you just look at that thing down the x-axis and then you just sort of figure out what the moments are about the x-axis, and then you look at the thing down the y-axis and figure out what the moments are about the y-axis. Or you can do vectors. I don't know, whatever you like. If you can't visualize things, then you're stuck using vectors. If you can visualize, I think you might like that better. I tend to be a visual person. I kind of like that better. Why don't we do it both ways? We got 15 minutes. No, we only have 7 minutes.
Race to the top.
So why don't we have two groups, one group doing it using scalar, one group doing it using vector, and see if you get the same answer. Who wants to do vector? Isaac? Just one?
I'll do it with Isaac.
So Jose and Isaac will do vector. And we could have 3 groups. So the other 2, you guys can do scalars, and another group can do scalars if you want to. Or I guess you have 3, maybe 3 doing scalar, 3 doing vector.
I'll do scalar.
It is.
They're doing vector.
So if you're doing vector, what you would do is you would want to actually specify
Which is which one? Which points?
F1, F2, F3.
Oh.
F1 is 100 Newton K, right? F2 is minus 500 Newton K. F3 is 400 Newton K. Yes, negative K.
So instead of putting it like this, you do it by
Yes,
force.
you're doing a resultant that way, and that's fine. You'll get that later,
Won't work, though.
but you have to, well, actually, you're finding the resultant, which is true. And your resultant, this is for the resultant, right? This is for FR. You can have an X, Y, and Z of this, right? And this works out to be what? Minus 800?
It's just helpful if you have.
So FR equals minus 800 K, right? Now you got to do the F1, F2, and F3 as vectors, right?
Yes.
And then you got to do the cross products.
Oh, right.
And so the R, I guess we're going to call this, what do we call this thing? The position vector for, where this thing goes is going to be, let's call this P again. We're going to put it location P or something, right? So R sub P is going to equal a vector. What's the vector going to be? Well, it's going to be XR times I plus YR times J. You with me? You're going XR in the I direction, right? You're going YR in the J direction.
Right.
You with me? That's the R sub P.
Precision, right?
That's P is the location where we're going to have to plant that force, so it has the same effect as these individual forces,
Right.
right? So this is our resultant. Now this has to be equivalent, whatever we decide for XR and YR has to be equivalent to the cross product, RP cross FR. Let me get that little, RP cross FR has to equal, well, you can figure that out, has to be the same as the sum of all the cross products of each force and their position vectors. Okay, so do it.
That's a mess.
Messy, right? But you can do it. And it's good practice working with vectors, because you never know. Sometimes you just have to use vectors.
So we have to cross every
So call F1. So the sum of the moments, you know,
Now,
let me just do this again. Sum of the moments at O, vector moments, in system 2
so then,
equals that. System 2 is the reduced system. System 1 is the original system. Sum of the moments about O in system 1
I think all we have to do is
F1.
continue.
two,
Yeah, F1.
three.
Yeah, and if you want, you know, F1 equals,
can we just look at it down?
I'm doing the whole thing for you, right? 100
So-
I, right? And what's R1?
This is what?
I.
Nope. What is
Yeah, I
R1?
guess so.
The position vector to the
Oh,
origin.
3.
3,
Yeah, no.
actually this is K, isn't
Yeah,
it?
that's why I was like.
100K, this is 3I, right?
So you call
So do it for,
0, 0.
so keep going, right? Do it for F2, do it for F3, and then do all those moment cross products.
Yeah, this one.
Yeah, you can each do your individual cross products.
So,
You need a better marker. There's probably, but try that green one over there.
well, because you don't have stuff in the Z plane. You're only in the X, Y. You don't have stuff in the X, Y. So, well, I mean, if you look at just the Y, Z, or the X, Z. So if Y is coming out like this.
Yeah, you got 100 Newton going up 3
Yeah,
meters
right.
away. You got 500 Newtons going down 4 meters away.
This is 3 meters.
Oh, yeah, because if you're looking at it like that, 400, this is
This is 5. Yeah.
Yeah.
Wait, so then I don't.
Come back to you guys. Now you don't really have to use a determinant. Well, actually you do probably because yours is a little bit misplaced. Yeah. But if you just have one component each, you can kind of, you know, you're doing R cross F. What's I cross K?
What did you say?
What's I cross K? You don't really need a determinant for that. I mean, you can if you're in doubt, but you should be able to do I cross K using your hands, right? I cross K.
Yeah, I just use multiple.
Your fingers are going from I to K.
I just wanted to.
What's I cross K?
In K is
Oh, I guess we can just add
negative.
Close. Negative J.
Negative J.
What?
Because your fingers got to go from I to K. I cross K. What?
I hate how
This is I and this is K.
Yeah.
So you got to do the R first.
Oh.
It's not F1 times R, it's R cross F.
Okay.
It's happening at you too. It's R cross F.
That would explain the sign.
Oh, this is better one.
This one's stuff.
Bummer.
Ron Marcus?
Oh, you got a good one. Oh. So I guess we have to find some of the moments.
When you're looking at it straight
That's
on,
about the y-axis there, right? This is the y-axis there.
Yes.
how would you write 500 and 400 if it's the same
What do you mean?
viewing plane? Like, it's 500 if you look at it.
Well, you could add them together.
Really? Oh, because it's like essentially.
Yeah. So it's essentially 900 going down, right? Oh, was one going up? No, they're both going down, right?
Oh, yeah. So there's water down.
But that doesn't give you a moment.
Yeah, that doesn't.
So you can leave it there, but
So do I not even have to write 100 on
This is 4 out.
can you see the 100? You can draw it, but I mean, you can do the moment about the x-axis, but it's
Okay, got it.
kind of helpful to just have everything there, just so you know you're not forgetting anything, right? And you can do some of the moments about the x-axis, right?
So like, is this?
That's system 1. That means the original system. System 2 is with our resultant.
Got it.
You got it?
I think so.
Wait, no, this is Y.
Okay. I'm getting hungry, you guys.
Me too.
This is Y.
I don't think we're going to be able to finish either one of these. Now, there's a problem exactly like this in the video.
Yeah.
So you can look for it and watch it and do this problem maybe while watching the video.
Yeah.
It's going to show you the scalar approach, I think, and then I might do the vector too. I'm not sure. I'm getting hungry, and you guys are not really impressing me here. I think it's going to take forever. I won't be eating until 2:30 at this rate. Why don't you take photos and pick up? Yeah. We'll finish it up tomorrow, maybe.
Yes.
And Savni, there's something wrong here. So your F3 is actually in the K direction.
Oh, Z.
Yeah, these are all K, and the R3 is
Oh, so that's what I was getting to.
R3 is in the J direction. Yeah, so this should be K. And if you're doing, and you can do this visually too, even though it's vectors, right?
Yep.
If you've got a, if you've got a K
Videos on like just
and a J, you're doing J cross minus K. Can you do the right hand roll to do that? In other words, your fingers are going in J, and they're going to rotate to minus K. That's how you do these things. You're doing R, which is J, cross minus K. Let me mark it again. So in other words, you're doing, J and minus K.
And
So which way is your thumb going? If your fingers are going from J to minus K.
towards K. Negative K. Because X, I will be your.
If your fingers are curling from J, your fingers are curling from J. There's your fingers. Which way is your thumb going on your right hand? If your fingers are doing that, put your fingers going from J to K. J to minus K. Which way is your thumb going?
That way.
Going into the board. Which direction is that?
Negative K.
Minus I. This is the I direction
Okay,
going
so
into
I
the
is
board.
facing towards-
I sort of coming out, yeah. So it's minus I. That should be your answer for that cross product. All right. So I have to say the quizzes were mixed. Did you read your grade yet? Good. Check out your quizzes. I provided a rubric showing you what I was looking for and the solutions. Even if you got 5 points, I'm showing you the solutions because you might want to look at it. But remember, a free body diagram is free from everything surrounding us. A lot of people are drawing cables and pull, and all the stuff that doesn't really belong there. You really should just have the forces acting on that knot. Yeah. And if you're worried about this, I'm going to have some extra credit stuff for you to do. So I'm going to be brutal on these quizzes, but I'm going to give you extra credit options so that you can keep practicing. But I don't think I'll have any extra credit options for free body diagrams because they're kind of a pain to grade. But once you know what I'm looking for, you should anchor that and do that. But you will have other ways to get points to make up for that.